Well, welcome to Chapter 3, how data is transported over our networks. Now, if we think back, we look at Chapter 1, we learned what a protocol was, and we learned that protocols are rules that govern how data travels across a network or a modem. Chapter 2, we learned about the application and network layer protocols and how protocols determine where to send our data in the instructions. We learned about the tasks associated with each layer of the OSI reference model, such as formatting and addressing and error correction. This chapter focuses on how the application data and instructions get from one host to another at the transport and network layers. We're going to learn how the protocols work at each of the two layers and how the routers work at the network layer. And then finally, we're going to learn about troubleshooting some of our routing issues. All right, now if we recall that the TCPIP is a suite of protocols, which means it's a great number of protocols all packaged into one, what we call protocol suite. Now that includes everything from your TCP to your IP, which is your IP version 4 and your IP version 6 addressing, the UDP protocols, the ARP protocols, what we call ARP, and many others. Now, what we do have to remember too is that TCP/IP itself is what we call open, which means it doesn't need a license for us to use it. It's open for everyone to use and it's free. And it's routable, which means that the information that we have in our packets can actually traverse or go across a router, which is important because of our older type protocols like NetBIOS and AppleTalk were not routable, which therefore meant leaving your network with that data packet virtually impossible. Now, also remember that TCP/IP protocols, they add a header to the data, which means they just add some information. So if we look over here on the one side of our packets, we have our data, which is what we call the payload. And then as we get down, after we get down from the application to the presentation to the session layer, when we hit the transport layer, you see we have our payload, but now we have the header here, which is more information about that transfer, the transport layer. So what we want to do in this section is, if we want to get into the details of all the content of the headers that we use in the transport and the network layers. So first we want to summarize everything we learned in Chapter 1 about the headers and the trailers, and you can see all that in here. And then we want to look at the receiving, how the receiving host over here de-encapsulates the data. So what that means is, as we went down the layer over here on this side, we added a header, okay? And then we added a header, then we added a header, and we added a trailer, okay, the frame, okay, we encapsulate all the data. When we get to this node over here, this guy is actually going to take the header off and the trailer, read the information, and then send it up to the next layer, to network layer. This layer here, he's going to tear off that header to be able to read the information and make sure it's for him. And then over here on the next one, he's going to then tear off the transport layer and then close the session with the sending node as it moves up and down the OSI reference model. This is a little something that we call peer networking, not like peer-to-peer as in the way that you guys did your lab the other week, but more of peer as in the physical layer here works with the physical layer here, and the data link layer here works with its peer on the receiving node here, and so on and so on and so on. Okay. What we do also need to recall or remember is that TCP, the Transmission Control Protocol, is a connection-oriented protocol. So what that means is that the protocol actually cares on whether or not you receive the data. And that's important. You see, because what happens is there's a three-way conversation that's going on in our network. And the first conversation is, hey, I've got some data to send to you. The second conversation from the receiving node is, Well, I'd like to acknowledge the fact that you have some data coming to me, and this is how much data that I can receive right now, and the speed in which I can receive it. It's kind of like when you and I are having a conversation. If I'm talking too fast, then you don't really understand what I'm saying. So perhaps I need to slow down the conversation so that you can understand what I'm saying. And maybe at times I have to shorten the amount of data that I'm giving you at different times so that you can comprehend that data. The same way you and I have a conversation is very similar to the way that our computer networks work. The receiving node may only be able to receive so much data at a time before it's overwhelmed. It may only be able to receive it at a certain speed before it doesn't understand what's happening. It can't translate, can't convert our information. And that's the exact same thing that happens with what we call a connection-oriented conversation. Another thing that goes along in here is a little something that we call sequencing. You see, at the transport layer, we take our data and we break it up into chunks. Now we take those chunks of data and we put numbers on them. See, when we do routing chooses the best path to get our data from point A to point B. Now, since our data sometimes might take a shorter path and another time might take a longer path, sometimes our data will get there out of order. So the packet that I send first might actually get there second, or the packet that I send second might actually get there sixth or seventh. So when it all gets to the end and we're finally get all of our data there, we have to put all of our information back in order. And that's a little something we call sequencing. We have to sequence those segments. And then how do I know I have it all there? Well, at the beginning of the data transmission, we decide to send some information that says, this is how much data I'm going to be sending you. And at the end of the transmission, we're going to check the information that came in. Then we're going to add up all the numbers that came through. And then if we think about it in simple terms, the answer to an addition problem is the sum. So what we're going to do is we're going to check to make sure that all our information is there. It's called a checksum. So it's important also that, as I mentioned earlier, when we're governing or we're determining the speed of our data and how it's going to get there, it's important for us to remember that we have a little something called flow control. That's the speed in which everything is going to get there. All right, now if we go back again and we talk about that connection-oriented conversation that we were having, and I told you that it was called a three-way handshake. So there's three transmissions that are sent before we actually send our data. The request for a connection, the respond to that. So the first one was that, see that SYN there? Well, that means synchronization. We're requesting a connection to be synchronized. Next thing you're going to do is you're going to have to come back to me and say, okay, we're synchronized, and I'm going to acknowledge the fact that it's synchronized. I'm going to kick back another acknowledgement saying that I received your information. After these three messages are sent, then I can segment my data, my payload, and I can start sending it out to you. And I give each of my individual transmissions a particular number, which, as I mentioned earlier, is our sequence number. And then here's an example. Now you'll notice here we have a sequence number that we tacked onto our packet, and then we also have an acknowledgement number. Please notice that the acknowledgement number corresponds to the sequence number sent, but the sequence number in the second conversation, the one right here in the middle, okay, this guy, he's got his own set of patterns here, okay. His sequence and acknowledgement match up here, and then in this one here, his sequence and acknowledgement match up here. Okay, that is how the three-way conversation occurs. So up until this point, okay, no payload has been included in any of the 3 initial messages, and the sequence numbers have increased by exactly 1 in each acknowledgement. It is a way for us to manage and keep track of these conversations. Okay. So next I want to talk about is something called a UDP datagram. Now UDP different than TCP because UDP doesn't offer any error checking, doesn't offer any sequencing. Okay. Now, a lot of times they'll call UDP more unreliable because it's connectionless oriented. The connection oriented is best effort guaranteed delivery, where a UDP connection is, well, I gave my best effort. Basically, it just throws the data at you and hopes you catch it. That's what a UDP. But the thing is, and the benefit of UDP is that UDP is faster and much more efficient. So think about it when, say, you're streaming video online. You know, being the YouTube generation, you watch a lot of YouTube videos. YouTube wouldn't be as exciting or worthwhile to watch if, say, it was always stopping and buffering. So as the screen states, UDP is more useful for your live video streaming, your live audio, because we don't want to be buffering, and we definitely want to make sure that all of our packets are going to get to their destination at the same time. Sometimes they don't. Sometimes the packet will fail. If you've ever been watching a video stream and all of a sudden it pauses for a brief moment and then it catches up and it's almost like you missed a full second of programming, chances are a couple of the packets got lost. They will not get resent as if they would with a TCP conversation. And UDP and IP are what we call connectionless oriented. Okay? IP operates at the network layer of the OSI reference model. It's what enables TCP/IP to inter-network, which means leave one network and go to another network. It is unreliable. It is connectionless, as I mentioned. Okay? Now, it doesn't guarantee delivery of the data, but what it does ensure, it ensures the data packets are being delivered to the correct address. We're just not ensuring that all of the packets are being delivered to the correct address. Okay? Now, I'm not going to cover the actual data frames for UDP and IP version 4 in huge detail, as this really is just an intro to networking class. Okay. You can read all about this in your books if need be, and you'll see the size of all of our packets. Okay. Now, what's really important, though, is when we look at the IP version 6 here. Now, you can see there's not as much going on in the IP version 6 as there is in the IP version 4. And this is one of the things that I try to get everyone to understand, is not only is the IP version 6 our newest form of computer addressing or network addressing, not only is it more efficient, but if we take a look, there's less going on. Now, if you can remember back to when we had our 3G phones and how our 3G phones were so much slower, but when you first went from your 3G phone, which you thought you had killer internet access and your awesome phone, and then you got your first IP version or your 4G phone, and it was like lightning. Well, I can tell you this, folks, the data is not moving through the air any faster. What we've done is we've packaged the data differently. So we actually have a larger packet going through the network as opposed to a packet with a whole bunch of just more data going with it. So another way to explain that would be, let's say you go to the grocery store and you've got a minivan. Well, you can fit a lot of groceries in the minivan. Let's say you go to the grocery store and you've got a smart car. You cannot get a lot of groceries in the smart car. I can carry more groceries in my minivan than I can in a smart car at the same speed. So therefore, IP version 6 is the minivan, IP version 4 is your smart car. Just one way to look at it. Like a tractor trailer going down the highway at 65 miles an hour and your smart car going down the highway at 65 miles per hour. They're going the same speed. One can just carry more data. One can carry more information. Okay? IPv6 uses a different packet format than IP version 4. Okay? Now we have something called the Internet Control Message Protocol, ICMP. Now you have all seen ICMP before. So where have you seen ICMP? Well, if we just look at the definition, ICMP, Internet Control Message Protocol. When you have done your labs over the past couple weeks, you may have noticed that you had to do a little command called ping, P-I-N-G, or Packet Internet Groper. And what you received back when you did a ping was an ICMP message. It's at it's an application layer protocol that uses the network as well. It can indicate what part of a network might be congested, like a trace route. Okay, we receive those messages. If data fails, it'll say unable to reach its destination. Now, where a lot of times we get confused is we look at the end line of our packet and we'll say, oh, well, 50% made it through and 50% didn't make it through, so I had a successful ping. You do not have a successful ping. You have to read the actual individual messages. You want to get a reply from the receiving node, not a destination host is unreachable. Now there's another little thing in here, another little acronym we have. It's called TTL right here, your time to live. Now the reason we have to have that time to live is because we have to make sure that our data will die out there. Okay, so if you say ping Microsoft.com and it doesn't find Microsoft.com, you can't have your data floating around the internet forever, because what will happen is it will collide with other data and then the internet goes down. So we always have to have a TTL, or time to live, on our data packets. Okay. Now if we do a ping, for example, and we get an ICMP message, but we also get ICMP messages on IP version 6. Now right now all of you have been working just with IP version 4, and you will eventually move on to an IP version 6 when we get into the other courses like the CNT120. Now there's another little acronym that we need to understand out here, and it's a little something called ARP. Now ARP stands for Address Resolution Protocol, and it's only used on IP version 4 networks. You see, when you and I are going to have a conversation on a network, it's important that I not only know your IP address, but I know your MAC address. Now if you remember or recall, that a MAC address is the 48-bit hexadecimal address that is assigned to every network card out there, whether it be your Bluetooth card, your Wi-Fi card, whatever. You have a unique 48-bit hexadecimal address, and it's called your MAC address. Well, there are times when I might know your IP address, but I don't know your MAC address. And if I don't know both of those addresses, well, then I can't have a conversation with you. So therefore, I have to send something out there called an ARP request. Now, the ARP request says, broadcast to everybody on my internal network, it will not go past the router. It says, hey, if this is your IP address, do me a favor and private message back to me your MAC address. So it broadcasts one way, but the address going back is just a single unicast address. Then we have the Internet Group Message Protocol. And the Internet Group Message Protocol on our IP version 4 networks operates at the network layer of the OSI model. It's used to manage our multicasting. And multicasting means that I'm sending data out to multiple users. Another way to think about that, for those of you who do internet gaming, or you do online chats with multiple people, that is a multicast going out to just a select group, say for a video conference, say for a video game. That would be an internet group management protocol, not message protocol, but management protocol. This is the slide for the ARP resolution protocol that I just brought up just a moment ago. Please remember that all of your devices have an ARP table. And what does that mean? An ARP table is nothing more than a list of IP address. It gets refreshes every 5 seconds to 30 seconds, and it refreshes and just keeps a list of all the devices on your network that you've been in contact with, so that you constantly have an updated message, so you don't have to keep sending ARP requests out, because the ARP requests are broadcast and they prevent other users on the network from being able to communicate. And so we don't want to send ARP requests out unless we truly have to.